from now on, things will really get a little bit different from what you have seen before. So, for instance, the first thing that has changed is the format of the slides. I was using some other type of slides before, but now we have a distinctly different format for the slides. It's also maybe to symbolize that things are changing from this week onwards. Okay, so basically we will start looking at multiple random variables. If you remember before, we saw that random variables are very useful ways to deal with the actual probability space, which may be very complex. So you look at functions from the outcome to a specific number, and then only look at that, and the distribution of that has something to say about what the probability space is, right? So this is very useful. And now we are going to start looking at multiple random variables. It turns out, you saw before that some usual outcomes and experiments that you study in practice are quite complex, and there are a lot of different outcomes that are of interest to you, and a lot of different random variables defined on the same probability space that are of interest to you. And these random variables could be connected because they are all defined on the same space. So how do we deal with that? What are the tools, and what are the definitions of distributions? How do you deal with the distribution there? How do you do computations with that? And how do you generally think about such scenarios is the main focus of week 3. Once again, we will see toy examples, we will see slightly more complicated examples, and maybe not too much of Python coding this week also, but let us get started with how to deal with multiple random variables in a probability space. Okay, so let us begin with a very simple example. Let us say you have a fair coin, let us say, and then you toss it 3 times, right? You toss it, pick it up, toss it again, pick it up, toss it again. So you will have 3 different outcomes for this, and naturally you can define 3 random variables, right? So here is a very natural definition for 3 random variables. I am going to call x1 as something that indicates whether the first toss was heads or tails, right? So this notion of indicating will be very useful. We will often define these type of random variables. They will take a value 1 if some event happens, 0 if some event does not happen. It is sort of like the Bernoulli trial random variable. These are very popular in probability. They appear again and again and again. Okay, so this x1 is an indicator for the first toss being heads, right? If it's 1 if the first toss is heads, 0 if the first toss is tails, right? And then now you can do x2, x3, isn't it? So x2 is for the second toss, x3 is for the third toss. Now these 3 random variables are defined on the same space, and here's a very ready-made example. So this is quickly pointing you to a very typical scenario where you will use multiple random variables, basically repeated Bernoulli trials, right? So when you have repeated trials of any sort, you are naturally going to have multiple random variables, and that is something that will show up all the time. Okay, and also you notice here something very interesting about the way these random variables are defined. If you take all 3 of them together, these things completely describe the outcome of the experiment, right? So the experiment is simple enough. It's a toy experiment, and you don't have a very, very complex outcome. And you define 3 random variables that sort of completely specifies the outcome. And another interesting observation you can make about this particular case is events that you define with x1, right? Supposing I define the event x1 equals 1. We saw before, right? The random variable taking a particular set of values or taking one value is actually an event. Now if you define an event with x1 alone, it's going to be independent of any event that I define with x2 alone, right? There are really only very few events we can define here. It's just 0 and 1, but still, x1 equals 1 is independent of x2 equals 1, and it's independent of x3 equals 1. So each random variable is sort of, even though all of them live in the same probability space, they are talking about independent occurrences in the experiment. And so if you just define events with each of them separately, they're going to be those events are going to be independent. Okay. So notice what I did there. That's like a short line in which a lot of things were going on. Okay, if you define event 1 with x1 and event 2 with x2, right? Whatever way in which you define it, these 2 events are going to be independent. Okay, so that's another observation you can make about these things. So this is a very typical setting once again where we will use multiple random variables to describe the outcome. Okay, so let's move on to something that's slightly more complicated, maybe a little bit more confusing. Okay, So this is like a lottery, you know, I mean, so you have a 2-digit lottery. We've seen this in one such problem before, but let's go back and revisit it again, okay. So you select a 2-digit number 00 to 99 uniformly at random, okay. So this is what you selected, okay. So this is already complex, I mean, maybe not that complex, but still it's a little bit more complex than the previous one, right. The previous one, there are really only 8 different outcomes. It's easy to deal with. Here there are 100 different outcomes, and there are 2 digits, and you can do, and there's a number that's coming out, and you can do various things with it. So you can extract a lot of partial information about this, the outcome that comes out of this experiment, and you can define random variables. Like for instance, I have defined here x to be the digit in the units place, okay. So you have 0099. Units place is the, you know, the first one from the right, and then you have the tens place. Those are the 2 digits, okay. So the first random variable I am defining here, this x is simply the number in the units place, okay. So you can take example. So supposing the random number is 23, x will take the value 3, okay. Now I am defining one more random variable. Notice what I am doing. Y is the remainder. I think there's a spelling mistake here, that's okay. Okay, so I'll underline it so that you can correct it later. So y is the remainder that's obtained when the number itself is divided by 4. Okay, so let's see a few examples. So let's say the number is 23. Okay, so for this guy, x is going to be, suppose the outcome is 23, then this will imply x is 3, and what will be y? So if you divide 23 by 4, you will get remainder 3, so y also becomes 3. So let's take another case, let's say 48, and for 48 you're going to get x equals 8, then y equals 0, isn't it? So likewise you can do, you know, in any number of things you can do, you will get, you know, x taking values from 0 to 9, and you can show in fact that x is actually uniformly distributed in 0 to 9, okay. So we'll see maybe later on some calculations, but this is not too hard to imagine, right. So what is probability that x equals 0? Probability that x equals 0 is the same as the 2-digit number being 00 or 10 or 20 or 30. There are 10 favorable outcomes, there are 100 total outcomes. To 10 by 100, it becomes 1 by 10. It's the same thing for 1 also. Probability that x equals 1, again there are 10 favorable outcomes, 0, 1, 1, 1, 2, 1, all the way till 9, 1, 10 by 100, it's 1 by 10. So all of them are equally likely, so x is uniform, okay. So likewise, maybe this is a little bit more complicated for you to see, but y will also be uniform in 0, 1, 2, 3, okay. I'll leave this as an exercise for you, but you can again check, right. So what is probability that y equals 0? What are all the favorable outcomes for you that result in y being 0? It could be 0, 0 or 0, 4 or 0, 8 or 1, 2 or 1, 6, like that, right. So all the way up to 96, all the multiples of 4 that are between 0, 0 and 9, 9, and you will see that's exactly 25 in number. So 25 by 100, you will get 1 by 4 for the probability that y is 0. Now for y equals 1, maybe you have to think a little bit more, but you can see what are all the numbers that will give you a remainder 1 when divided by 4. The first choice is 0, 1. Next it's 0, 5. Next is 0, 9, 13, 17, so on. So you'll see that again is also exactly 25. You take all the multiples of 4 and add 1 to them, you will get these numbers. That's again 25. Likewise, you will see for 2 and 3 also there's 25 favorable outcomes out of the 100, so you'll get 1 by 4. So x and y are uniform in their respective ranges, and their ranges are different, okay. So here is 2 different random variables that I defined on a common probability space. If you look at the dependence or independence, so previously when in the coin toss experiment, if I defined an event with x1, we saw that it was clearly independent of anything I defined with x2. But notice what can happen here, right. Supposing somebody told you the event x equals 1 occurred, okay. So x equals 1 has occurred, which means the last digit is 1, okay. And then if you were to look at the event y equals 0, okay, what do you think will happen here? Can y be 0 if x is 1? That's not possible, right. Any number that ends in 1 cannot be a multiple of 4. It cannot give you a remainder 0 and 4 when you divide by 4. So you see that this x and y, if you define an event with x, you define an event with y, these two events are not going to be independent. One will determine or affect the other, occurrence of the other. Occurrence of one affects the occurrence of the other, right? So that clearly shows that these two events are not independent. So this is a different type of two random variables. There are two random variables we defined here, and one seems to affect the value of the other. Okay, so this can also happen. All right. So we already saw two examples. One was a simple coin toss example where it appears that you define one random variable with the first toss, another with the second toss. Those two don't affect. And here we define something slightly more intricate with a 2-digit number, and we are seeing that one random variable can influence the other. Now this is important in practice, and I'll show you. We'll go to the next example to see how things like this can play a role in modeling and other things in practice. We go back to our favorite IPL power play over data. This is something that that's of interest to us. We've been keeping this as one common theme throughout the course. So here is once again, what's my experiment? It's 1 over of IPL power play. Maybe you take it to be the first over, for instance. I mean, if you want a specific example, okay, or maybe the third over or the fourth over, any particular over you pick, or maybe any over, right? All the possible overs. Okay. So here is here are two random variables that I've defined in this IPL power play over, 1 over of the IPL power play. The first random variable I'll call x. This is the number of runs scored in the over. Okay, the total number of runs scored in all the deliveries that were part of the over. Okay, so that's x for you. Then you can have a number y, the random variable y, which is the number of wickets that fell in the over. Okay, so once again, notice there are two different random variables. X is the number of runs in the over, y is the number of wickets in the over. Now, if you think of once again the IPL outcome is over is quite a complex outcome. So many things happen in the over, and you're not going to be able to model everything properly. But let's see if we can model x and y. This is of specific interest, isn't it? X and y are very interesting random variables as far as the entire outcome is concerned in this experiment. Okay, so if you look at the events y equals 0, y equals 1, y equals 2, y equals 0 is probably the most common. There were no wickets that fell, and y equals 1, 1 wicket fell in the over, and y equals 2, 2 wickets fell in the over. Okay, so this is something that can happen, right? It can happen in the power play if you have good bowling. Okay, so now notice what we can say. So there's this connection between x and y that you may imagine in your mind as a possibility when you model. Like for instance, supposing given y is 0, we expect x to take larger values than when given y is 1. Okay, and given y is 2, we generally expect x to take significantly lower values. So, no, it may or may not be true. Maybe the last 2 wickets fell in the last 2 balls or something like that. It could happen that way. Maybe all the runs were scored before that. But you don't imagine that to be likely, right? If the wickets are falling, and the runs are going to be slightly slower, so slightly lower, right? So notice how this kind of thinking and modeling from our side is helping in the understanding of data that comes from the IPL power play. Supposing you want to build a model for the IPL over, and then you want to think of these random variables, maybe you have to take these kind of things into account. So given number of wickets, maybe you want to modify the distribution for how many runs fell, right? So things like this. So you already see that in complex experiments, these kind of relationships, I mean, again, everything is random. It's no deterministic relationship. I can't write an equation of any sort, but still in the distribution, there is some understanding of what might happen if some wicket fell. Okay, so these kind of relationships are very important when you try to model complex experiments, and this is something that's routinely done when we want to write down distributions. Okay, particularly when you want to understand data, this kind of thinking is very, very useful. Okay, so hopefully I've convinced you that there are experiments, both small ones and big sized ones, where defining multiple random variables, understanding relationships between them, trying to model distributions and between these random variables is of great use. Okay, so how do we have what are the main objects that we can focus on when we want to jointly study multiple random variables? Okay, so that's what we're going to see next. That's the first part. Okay, so first we'll begin with two random variables, okay, just two. Okay, we'll go to more than two soon enough. You'll see there are many more you can define, but we'll begin with two random variables. Okay, in two random variables, it turns out. So you remember we had PMF for one discrete random variable. When you have two discrete random variables defined in the same probability space, you can have many types of PMFs. One is something called the joint PMF. The other is these are objects called marginal PMFs. The thirdly, you will have objects called conditional PMFs. All these three, one needs to have a good understanding and capability of manipulating. So previously itself we saw the one PMF had some simple conditions that it needed to satisfy, and you could play around with it, and then you could use it for various things. Now similarly, when we go to joint PMFs and marginal PMFs and conditional PMFs, you'll again have properties that these satisfy. There will be structure, conditions, relationships between them. All of them you should be able to write equations for and manipulate and solve and all that. Okay, so all that will happen in this section. Okay, so let's get into it. Okay, so first we'll define what a joint PMF of two discrete random variables is. Okay, so here's the definition. X and Y are discrete random variables that are defined in the same probability space. You can go back to the examples I gave you and think of specific examples if this is confusing you. So let's say the range of X and range of Y are known, I mean Tx and Ty. So we saw in the examples, it's easy to think of the range of a random variable once it's defined. Okay. Now notice how the joint PMF of X and Y is defined. We will first denote it as F. Within the subscript you will have XY. Okay, it's not, don't think of it as the product of XY. Now there is that confusion. It may be the product of XY, but usually that's not the case. So when I write F sub XY, invariably I mean the joint distribution of X and Y, joint PMF of X and Y. But it can happen that I'm interested in the product also. We'll come back to it later, but live with this ambiguity for once and it will be clear. So usually people will say the joint PMF fxy. So it will be clear to you what it is. Okay. Now what is this fxy? It's a function from the Cartesian product Tx cross Ty to 0, 1. Okay. And how do we define this function? It's defined. So fxy, the arguments are 2 now, right? Because it's a Cartesian product. There is a T1 that will come from Tx and there is a T2 that will come from Ty. For every T1 and T2, this fxy will assign a number. Okay, so you give me T1, give me T2. You give me a value in the range of X, give me a value in the range of Y. This joint PMF will assign a probability, okay, value between 0 and 1, it will be a probability to the T1 comma T2. Now contrast this with the PMF itself, right? PMF was one random variable, there was a range for that random variable. For every value in the range, the PMF of that point is simply the probability that X equals T. Now in the joint PMF we have two random variables, so clearly we need T1 and T2, one coming from the range of 1, the other coming from the range of 2, and the joint PMF simply assigns the probability of X equals T1 and Y equals T. Okay, I've put T1 here, T1 here, this is wrong, so please note this correction, this is going to become T2. Okay, probability of X equals T1 and Y equals T2, that's what happens here. Okay, so let me just make sure I make this correction, it's a little typo. Okay, so this is defined as the joint PMF. It's sort of clear what it is, and we'll see quickly some examples on computation to be sure we understand what the joint PMF is. Okay. So usually one can write it as a table or a matrix, right? So usually the PMF is written in in a table in one row, right? The value of X and then value of the PMF. So here you have two axes, T1 and T2, so you can write it as a table or a matrix. Okay. And notice this popular notation. Okay, so this notation is very important. So instead of writing this and complicating things, we'll simply put a comma. Okay, X equals T1, comma, Y equals T2. Okay, so this comma, don't interpret it as or anything, it is and. Okay, so this is both of these and the probability of that is the joint PMF. Okay, so let's look at some examples. You'll see it'll be clearer with some examples. Okay, we're going to look at a situation where you tossed a fair coin twice and you defined indicators x1 and x2 for the first toss being heads and the second toss being heads, right. So, this is the definition of that. Now, I know that the range of x1 is 0, 1, range of x2 is 0, 1, and if I were to evaluate f x1 x2 of 0, 0, right. So, this is the joint PMF of x1 and x2 evaluated at 0, 0, that is the probability that x1 equals 0 and x2 equals 0, isn't it. So, now remember, this is a fair coin toss twice and these are independent tosses, right, physically independent tosses. So, it is very natural to assume these two events are independent, right. So, x1 equal to 0 and x2 equal to 0 is independent. So, probability of the intersection and is basically product because of the independence. So, you have half into half, you get 1 by 4. Same thing with f x1 x2 evaluated as 0, 1. So, the joint PMF seems easy to evaluate in this case, isn't it? You just have to write down all the possibilities and simply multiply the probabilities, right, and that is because of the independence. So, independence is usually very, very easy, and now you can make our little table here, okay. So, this table, notice how this table works. The values of T1 are here 0, 0, and the values of T2 are here 0, 1, and this matrix or table is basically f x1 x2 of T1 comma T2. So, this 1 by 4, for instance, this 1 by 4 here is f x1 x2 of 1 comma 1, okay, easy enough, right. So, this is all that is to join PMFs, okay. So, once again imagine how this will generalize. Supposing x1 and x2 are two general random variables, you simply put all the values taken by x1 on the row, on the first row, all the values taken by x2 on the first column, and wherever you have the matrix in the ijth position, you look at x1 taking value I, x2 taking value j, then you write down what the probability of that is, okay. So, that is all it is, right. So, you can now build the PMF, and these are very useful things to write, okay. So, notice a few interesting and important properties. We'll look at them later as well, but this is easy, okay. Every entry, the PMF will take values between 0 and 1, right. So, that is very clear, and the joint PMF of course takes values between 0 and 1. If you add up the values of all the joint PMFs, okay, so all possible values in this table, if you add up, you are going to get 1, okay. So, these are two properties that will show up again and again. Each entry is between 0 and 1. Sum of all entries equals 1, okay. So, these are very important properties of a joint PMF. Any joint PMF will satisfy these two properties, okay. So, note it down, this is very, very important. Each entry in the joint PMF table, once you make it, it's going to be between 0 and 1. You add up all of them, you should get 1, okay. It's very, very important. Why should you get 1 if you add up all of them? Right, that exhausts all the possible values that x1 can take and x2 can take, and clearly that should be 1. I mean, any outcome, x1 is going to belong to its range, x2 is going to belong to its range, and if you add up everything, that basically tells you x1 belongs to the range and x2 belongs to its range. So, that is going to be 1, right. So, that happens in general, okay. So, let us look at the next example. We looked at this random two-digit number example. You remember x was the units place and y was the remainder that you got when you divided by 4. That is also called number modulo 4, I am sorry, okay. The number modulo 4 is basically remainder when divided by 4, okay. Okay. So, now you can do a simple little calculation. If you want to look at fxy of 0, 0, okay, this is the probability that x equals 0 and y equals 0. Number ends in 0 and should be a multiple of 4, right? That is what this means, okay. What are the favorable cases? You see 0, 0 and 1, 0 will not work. Why? 1, 0 is x equals 0, but y is not 0. It is not divisible by 4. You get a remainder of 2 when you divide by 4. So, 1, 0 will not happen. So you see 0, 0, 2, 0, 4, 0, 6, 0, 8, 0, all of these will satisfy both conditions as 5 out of 100, 1 by 20. Let's look at fxy of 1 comma 0, okay. You want the number to end in 1, right, x equals 1, and you want it to be a multiple of 4, y equals 0. Now this is not going to happen, okay. There is no outcome that will give you this, and you get a probability of 0 for this. So notice how this has gone on, some value is 1 by 20, some value is 0. So let's look at some other value, 4 comma 2, okay. Number ends in 2, okay, so I think I got that wrong. Number ends in 4, okay, seems to be a day of typos, okay. Number ends in 4 and number is 2 modulo 4, okay. What do we mean by 2 modulo 4? Reminder 2 when divided by, this is the same as, let me just write it in terms of y, this is x equals 4 and y equals 2, okay. So now you can sort of look at all the numbers. If you want x equals 4 and y equals 2, 14 will satisfy that, okay. So 0, 4 clearly will not when x is 4 but y is 0. If you go to 14, you will get that, okay. X will be 4, it ends in 4 and you get a remainder of 2 when divided by 4, okay. 34 will satisfy that, 54 will satisfy, 74, 94 will satisfy that. Again you get 5 by 100. It seems like it's either number is 1 by 20 or 0, right. No other number is probably going to work, and that's true, okay. So you can check out all the possibilities, and if you write down fxy of t1 comma t2, now notice how this is more general than the previous picture, pay attention to this. You want to make a table of fxy of t1 comma t2, you put the values of t1 here along these rows, put the value along the first row, and put the values of t2 along the column, okay, 0, 1, 2, 3, 4 all the way to 9, 0, 1, 2, 3, okay. And 0 comma 0 is 1 by 20, 1 comma 0 is 0, 2 comma 0 is again 1 by 20, 3 comma 0 is 0, so on, okay. So notice how this 1 by 20 and 0 alternate, okay. Now if you go to t2 being 1, 0 comma 1 will be 0, okay. Why is 0 comma 1 0? You can check that. If the number is ending in a 0 and you're getting 1 mod 4, that won't happen. If the number ends in 0, you will only get either 0 mod 4 or 2 mod 4, okay. So you can't get anything else, so it will be 0. But 1 comma 1 is possible. You can end in 1 and you can get 1 mod 4, right. So that would happen with numbers like 0, 1, 21, 41, things like that, okay. So you'd get 5 numbers once again. So you either keep getting 1 by 20 or 0. So, okay, you have to check this. Maybe it's a bit of a pain to check everything, but you can check in general, sort of argue writing down with expressions that this has to be the joint PMF. Once again, notice every entry in the joint PMF is between 0 and 1, and if you add up all of them, you will get 1, okay. You can check it out. You have 5 1 by 20s here, 10 1 by 20s, 15 1 by 20s, 20 1 by 20s, 20 into 1 by 20 is 1, okay. So both the properties are satisfied for the joint PMF, and it's also a reasonable joint PMF for this problem, okay. So notice how things are getting slightly more complex, and as you go more and more into complex outcomes, this kind of dependency is very crucial, and it will become more and more complicated to write down, okay. Okay, so let me stop here with the first part of the lecture. We will pick up with marginal PDFs in the second part going on.